Hello and welcome to another exciting lecture for research methods. In this lecture, we'll be talking about the experimental research strategy. Should be a pretty short one. So learning objectives we're going to cover here, and there is 7 of them and they go pretty quick. So we've got the first one is explain the goals of the experimental research strategy. The second one is list the 4 basic elements of experiments. Then we're going to differentiate the different types of variables in the experimental research strategy. Examine the problems with causation, examine the purpose of control in an experiment, explain the purpose of manipulation in an experiment, and finally consider ways to increase external validity in an experiment. So as you can see, a lot of this is just a continuation of the last lecture, but now looking at it specifically with the experimental research strategy. So getting right into that first learning objective, explain the goal of the experimental research strategy. So when we're looking at this, well, first off, what is the goal of it? And this should be pretty self-evident from what we talked about in the previous lecture when we had the 3 different kinds of studies. We had correlational studies, we had descriptive studies, and we had experimental studies. What were experimental also called? They were called causal studies. So the goal of experimental research is to establish the existence of a cause and effect relationship between 2 variables. Pretty self-explanatory, and you'll recall those things that you require, that you've got temporal precedence, that you've got a relationship, and that you've controlled other things. Well, that's what we're going to look at throughout this, is doing those things. So because, again, the goal is to establish that cause and effect relationship, which gets us to true experiments. So true experiments, as opposed to quasi-experimental design, which we'll talk about later in the semester, but true experiments must demonstrate that changes in one variable are directly responsible for causing, really important word there, causing changes in the second variable. So again, through those sets of rules that you need to determine causation, the true experiment does that. So we are going to, by using a true experiment, we are going to be able to identify cause. Which gets us to the second learning objective here. That is, list the 4 basic elements of an experiment. So we'll get right into these, but the 4 basic elements, they're important for the entire experimental design. You can't do an experimental design without these. So the first one is manipulation. This one's important because the researcher needs to manipulate one of the variables in an experiment. Something has to be manipulated. So you have to have manipulation. Through this manipulation, we are identifying or developing that temporal precedence we talked about before. Because if we do the manipulation and then we measure the variable, we are finding something that we changed can result in the measured variable. So the researcher manipulates one variable. This is also called the independent variable. The researcher then measures a second variable. So this second variable is the outcome variable. It's the variable that's measured afterwards, after the manipulation occurs. And this is the dependent variable. Then after that, a comparison's made. So the scores in one treatment condition are compared with the scores in the other treatment condition. And this is where through stats, you determine if there is an association, if there is a relationship. Through statistics, we determine if there is an association or a relationship between the 2 variables. And if it was just the association we were concerned with, then we wouldn't have cause. How can we determine cause? Well, the important thing is the last component, and that is control. We control for all other variables. There's various different ways we can control for them, as we talked about before, one of the biggest being random assignment. But if we are controlling for all other variables, we're sure that the relationship between the 2 variables is due to the 2 variables and our manipulation. and not due to just the association, though again you have to have the association. So because of that, you can determine cause. You can determine that the independent variable causes the dependent variable. Third learning objective, differentiate the different types of variables in an experimental research strategy. So I just said these, but we're going to go over them now in a little bit more detail. So the independent variable is whatever variable is manipulated by the researcher. It is the treatment condition. So whenever you're assigning people to groups, you're assigning people to watch one video or another video, you're assigning people to play one video game or another video game, you're assigning people to get one drug treatment or another drug treatment, you're assigning people to get one therapy treatment or another therapy treatment. You're assigning people. So you're manipulating that variable by assigning people to these groups. Then we'll have levels of the independent variable. And the levels of the independent variable are the different treatment conditions. So I've been using examples with two groups here. You give them drug A or drug B, but you could have more than that. You could have drug A, drug B, or drug C. In that case, you'd have 3 levels. And you select our levels, our different groups, to create and define the treatment conditions. Whatever you're trying to see if there's a difference in, or even sometimes you're trying to see if there's a similarity between, but you're still in that case trying to see if there's a difference between by looking at the opposite of it and hoping you don't find a difference if you're trying to find a similarity. But the point remains is that you determine how the groups are made up by your hypotheses, by your theoretical background. So that's the independent variable. Then the dependent variable is the measured variable. It's the variable that is assessed to see if the effects of manipulating the independent variable. So this is the measured variable. And the independent variable is the manipulated variable. So those are the two main variables that we like in our experiment. Then there's the variables we don't necessarily like, and that is extraneous variables. So you'll hear them called extraneous variables is typically, but sometimes you'll hear them called confounds. Because typically confounding extraneous variables are the ones we're concerned with. But an extraneous variable is all other variables in the study other than independent and dependent variables. And an extraneous variable becomes a confounding variable only if it influences the dependent variable. So if it's just, let's say you're looking at something else that has no relationship with the dependent variable. Let's say you looked at gender and their gender is not an effect on the dependent variable. Gender would be an extraneous variable that would not be a confounding variable because it has no effect on it. The things that are bad are these extraneous variables that do influence the dependent variable. So when we do have confounding variables, what we want to do is make sure that these variables vary systematically with the independent variable. So it's a variable that changes randomly with no relation to the independent variable. If it does that, it's not a threat. Let's say gender does affect our dependent variable. So we've got an extraneous variable that does influence the dependent variable. But let's say gender affects it, but we assign people to groups such that each person has an equal chance of being in group A or group B, and we get gender differences in those two groups that are equal or roughly equal because of randomness. Sometimes there'll be little differences there, but by randomness they should be roughly equal. Then that variable's effect on the dependent variable becomes systematic. It's systematic with the independent variable, meaning each level of the independent variable has an equal chance of having people with that confounding variable and people without that confounding variable. So as in that case, it's not a threat. It's still a confounding variable, but it's not a threat to our experiment. Which gets us to the fourth learning objective. It's the third variable problem. So again, we're trying with our experiment to establish that two variables are related, and we're doing that through those steps, that temporal precedence. But we're checking the association statistically. If we find a relationship, it doesn't necessarily mean that there's that direct causal relationship. A third unidentified variable may still be responsible for producing the observed relationship. What do I mean by that? Well, there's a couple things that we'll look at, but sometimes confounding variables still come up. Even if we've tried to control for everything, sometimes confounding variables still come up. An example of this is, I told you guys about some of the research I did in the past on hockey players, looking at how facial width to height predicts aggression, and found that in some cases it worked, in some cases it didn't. And through studies that followed that, through subsequent studies, we found out that facial width to height does have a causal relationship with aggression, but it's not direct, meaning there was a third unidentified variable that is responsible for that relationship, and that being social status or relative social status. So it's possible where you can sometimes find a relationship, but it might not be directly causal, it might be indirectly a causal. So because of that, you have to consider variables in the problem, especially when you get results that are not significant but close to significant. And then you can go through and look for variables that might be causing or producing that observed relationship between your two variables. So this gets us to examine the problems with causation still, and looking at the directionality problem. So with the directionality problem, we're looking at, again, we may establish a relationship between the two variables, but the existence of a relationship does not always explain the direction of the relationship. So the problem is to determine which variable is the cause and which is the effect. And again, we're now circling back to an experiment. When we have an experiment and we manipulate an independent variable prior to the change in the dependent variable, then we measure the dependent variable and we find a change, then we've established temporal precedence, as long as we are creating our groups in the independent variable in such a way that we are eliminating the possibility that the causation goes in the opposite direction. And we do that, again, like I've said before, by doing things like random assignment to groups. Which brings us to learning objective 5, and that's explain the purpose of control in an experiment. So again, I've said this a few times, but this is, so we do temporal precedence, we do association, and then we need control. We need to control for those third variables. We need to increase our internal validity. Internal validity, if you'll recall from the last lecture, is that control. So the two variables must be isolated from the influence of other variables, and the exact character of a relationship must become clear. So this is where, again, like I was saying, we must isolate them, and we do this by essentially setting up an experiment in such a way that all of these possible extraneous variables are the exact same for all participants in the study. If I give the first group their drug in the morning, I need to give the second group their drug in the morning. Why? Because then I'm controlling for time of day. Time of day may have an effect on how the drug affects people. If I'm giving people a test, I must give them the test in the same room, with the same lighting, with the same temperature, with the same sound, with the same instructions. Because even if I've split people into two different groups with two different things that maybe happened before they came in the room to take the test, the point is by controlling for everything else other than the thing I manipulated that happened before they came in the room to take the test, then I am controlling for all of these other variables, so I'm isolating the influence of the variables. I'm isolating the influence of other variables, and I'm isolating it to the influence of the independent variable on the dependent variable. So you recall those three goals in demonstrating the cause and effect relationship. These are the ones I've said a few times today. We talked about it in the previous lecture. But first is you have to demonstrate that relationship between A and B, or covariance. So you must have covariance between A and B. You must have temporal precedence, meaning the independent variable has to come before the dependent variable. So temporal precedence. The independent variable has to come before the dependent variable. And finally, and this is the one we're talking about now, and that is control, or internal validity. You have to establish that the one specific variable is what's responsible for the changes in the other variable, or internal validity. And again, we do this via control. We have to rule out any extraneous variables by controlling for those extraneous variables. So the next thing we're going to talk about is manipulation in an experiment. So now we're going to look kind of at the experiment as a whole from the beginning, and then be able to look at manipulation and directionality and control and all of those. So the first thing is manipulation. So this is where we determine the levels of the independent variable. And we create from that a set of treatment conditions corresponding to the levels. So again, let's say we were trying to see if a new drug reduces pain better than an existing drug. So our two levels of the independent variable are the new drug and the existing drug. And we set the treatment conditions, that is, one group is going to get drug A, one group is going to get drug B. Seems pretty simple, and it actually is pretty simple once you get used to it, but you just got to realize that when we're talking about this manipulation, we're talking about setting our levels of the independent variable. And because of this manipulation, it allows us to determine the direction of the relationship through temporal precedence, meaning I do the manipulation first. So the levels of the treatment condition, drug A or drug B. I put people into drug A, I put people into drug B, I give them drug A and drug B, and then I measure their outcomes. Now, you could say that the only reason the measurement of the outcomes is coming after is because I measured it after. But the important thing to note is that if you manipulate your groups correctly, you assign people to the groups correctly, then you could measure the variable before and the difference between the different levels. Let's say we had an A and a B. Before, they should be the same. Why? Because if we manipulated, or roughly the same, if we manipulated our groups correctly by randomly assigning people to be in group A or group B, then their pain levels before taking the drugs should be roughly equal. But then after, they're different. At least that's what we're hoping that they're going to be, is that they're different. Because, again, then the administration of the drug comes first, temporal precedence, and then the measurement of their pain after. And sometimes you'll actually see this. Quite often what you'll see is not interested in their after levels of pain, but in their change in pain, or delta, change in pain levels. So they take and measure before, administer the drug, and then measure after, and the change will be attributed, because the only thing that's supposed to come between the before and after is the administration of the experimental condition, the independent variable. So that change in their level of the dependent variable will have to be as a result of the administration of the independent variable. as long as people are randomly assigned to groups. So again, we've got this, the manipulation and directionality. When we look at it here, let's say we're measuring ice cream consumption and temperature. Well, if let's say I made the ice cream consumption the independent variable, and I gave one group of people ice cream, and one group of people like a glass of water, something else similar but not the same. Well, then, or a bowl of chili, let's say. But then we would then measure the dependent variable, and there'd be no association there because eating ice cream isn't going to change the temperature outside. However, what if I made temperature the independent variable and put bowls of ice cream in the room and used that as how much people ate as a dependent variable? And half of the group went into a room that was 80 degrees and half of them went into a room that was 60 degrees. Well, then by manipulating temperature first and then measuring how much ice cream is consumed, you can get temporal precedence. You can get directionality. As far as manipulation in the third variable problem, this is where, again, you want to control other variables other than the independent variable and dependent variable. So in a sense, like it says here, the observed relationship that you find can't be contaminated by the influence of other variables. So researchers must do everything they can to eliminate these confounding variables, even if basically the way you would eliminate them is by making sure that the third variable changes systematically with the variable being studied. Meaning it's if you've got, let's say, that ice cream and temperature. So temperature's in one, ice cream's in the other. And let's say lactose intolerant would be a confounding variable because people who are lactose intolerant aren't going to eat any ice cream. Well, if you assign all the people that are lactose intolerant to the hot group and all the people that are not to the cold group, then in that case, you're going to end up with the people who are not lactose, the colder group, being the one who eat more ice cream. So what you need to do is, like I've said a few times, and we're going to continue saying this, is random assignment. If you randomly assign people to groups, then you should end up with roughly the same amount of people that are lactose intolerant in each group. So then that variable is now systematically controlled for, because if you have somebody that won't eat ice cream in the warm group, you should have somebody who won't eat ice cream in the cold group. And that works for all of the different confounding variables. So, because manipulation there can be used to control the influence of the outside variables. We get in temperature that affects a couple different things we know of. Ice cream consumption and crime rate. Why is this a point? Because it has been found that ice cream consumption and crime rate are correlated, even before we look at temperature. So let's even ignore temperature for a second. Ice cream consumption and crime rate are correlated. Does that mean one causes the other? No. And as we know, temperature is something that we've been able to experimentally manipulate that causes both of these. So if there is a relationship between ice cream consumption and crime rate, we can control for that relationship, in a sense, by using a controlled experiment and manipulating temperature that way. What are our three primary techniques for controlling extraneous variables? One is holding a variable constant. So this is a statistical constant. So we'll hold a variable statistically constant, meaning let's say we know gender's a confounding variable. Well, there's a way statistically, granted we do random assignment. We'll get to that with number 3. But the point is you might still have differences between your groups. What you can actually do is, if you know gender is a confounding variable, what you can do is a statistical technique where the stats in the Excel or SPSS or whatever stats program you use, the stats program will control for that third variable, that confounding variable, meaning it will statistically account for it when it's looking at the relationship between your independent and dependent variable. If it will make it so that it varies in kind, meaning that it's going to, the variance is going to stay the same regardless of if gender is present or not. So it's a way to statistically control for. Though the stats behind it is beyond the scope of this class, but the point is there is a way to statistically hold constant variables. You can match values across treatment conditions. Let's say you've got, again, you know gender is a confounding variable. So instead of holding the variable constant, what you can do is make sure that you've got an equal amount of men and women in both of your treatment or in all of your treatment conditions. Let's say you plan on having 100 participants. You can make sure you have 25 men and 25 women in drug A, 25 men and 25 women in drug B. And by doing that, you're matching values across the treatment condition. So in a sense, you are controlling for that variable. And then the final thing is using randomization. So using randomizing, you basically make sure that, and it says to help avoid a systematic relationship between the two variables, but you're making it so that the error is systematic, meaning that the error is the same, the effect of that variable is the same in all treatment conditions. So and again, this is our most powerful tool for controlling extraneous variables, because in both of these, both 1 and 2, you have to know. You have to already know what the confounding variable is. To match for it or to control for it, or to match for it or to hold a variable constant, you have to know what variable that is. You have to know it might be gender. The problem is there could be many, many variables that we don't know whether they're going to be a confound. So instead, we do random assignment, randomization. Every single person in our study has an equal chance of being in each of the groups. By doing this, we are essentially matching the groups for the most part. We are matching them through randomness. So if you do that, let's say you get 100 participants and you put 50 in each group randomly, you should have gender ratios in the two groups and the two treatment conditions that are roughly similar. You might have small differences, and small differences are fine, but they should be roughly similar overall. So what are the advantages and disadvantages of these? So holding constant and matching requires extra effort or extra measurement and knowing the variable that's going to be held constant or matched on. So because of that, it limits our external validity. We can't generalize as well to the external population because in our study, we held a variable constant. We matched for a variable. Because of that, we can't generalize to the general population because in the general population, that variable is not held constant. Which gets us to randomization. Randomization will control for a wide variety of variables simultaneously, ones we might not even know we're controlling for, but it's not guaranteed to be successful in balancing variables. What do I mean by that? I mean that if let's say gender was a confounding variable, there's no guarantee that through randomization we're going to have roughly equal gender ratios in our two different treatment conditions. It could just be by random chance we get a whole bunch more guys in one and girls in the other. So because of that, it's not always guaranteed to be successful in balancing variables because it's based on probability. There's always a probability that you're going to get unmatched groups or unbalanced variables. So let's look at the addition of control groups in a true experiment and how control groups work as manipulation checks. So in an experiment, our experimental condition refers to the treatment condition of our variable. The control group will either refer to a no treatment condition or, and there's a couple different types, we'll look at those in just a second. We'll come back to what this experimental group is in just a second. But the control group typically refers to a no treatment condition in an experiment. Now, one way you can have it is truly no treatment, where the participants in it do not receive any of the treatment being evaluated. They don't receive anything at all. Quite often, though, instead of a no treatment condition, which we'll get is a placebo condition. So they'll be given an ineffective treatment that has no medical effect. And we've talked about this before, but the placebo effect is basically what will occur when people think the medication is effective. So let's say we give drug A that's a pain reliever and drug B that's a sugar pill, but we tell them it's a pain reliever. Well, the placebo effect, the people who get the sugar pill will still have a reduction in pain. That's due to the placebo effect. It's a lower effect, though, than typically what a true drug's effect would be. So that's what we're trying to see in this case. We're trying to see if our drug A is actually more effective than just the placebo effect. And the whole placebo effect, it depends on the type of research we're doing. Outcome research that investigates the effectiveness in treatment has the goal to determine whether a treatment produces a substantial or clinically significant effect. So what that means is even if a drug has an effect, let's say we give drug A to people and it has an effect, and that effect is actually even slightly more than the placebo effect. But that drug has side effects, or the effect is just barely more than the placebo effect. Then that drug isn't a good drug because it has a insubstantial or a non-clinically significant effect. It has an effect, but its effect isn't big enough to justify the side effects or the risks of giving and the expense of giving that drug. Then process research attempts to identify the active components of the treatment, and then for this, the placebo effect must be separated from other active components of the treatment. So through this, we're trying to find out what is actually going on. It could be that in our drug, that part of the effect of the drug is just the placebo effect, and the other part of the effect of the drug is the drug itself. And we need to be able to separate how much of an effect comes from placebo and how much of it comes from the drug itself. Now, these are two types of control groups. There is a third type of control group that doesn't get talked about here, and that third type of control group is a comparison group. I'm going to just write it down here. Who receive an existing treatment. And within that, we have what's usually called a gold standard, meaning that other treatment condition is a gold standard. Let's say we're trying to see if a drug has a pain relief effect. We probably wouldn't compare that drug to a placebo. Why? Because it would be unethical to give participants something that isn't going to reduce their pain. We're not interested to see if our drug reduces pain. We're interested to see if our drug reduces pain better than existing methods. So instead of making our control group be a placebo or no treatment condition, we'll make our control group be the existing gold standard for pain relief. In this case, it would probably be acetaminophen. So we would be comparing our new drug to acetaminophen, at least if we're looking for a minor drug reliever. If we're looking for a major one, we may compare it to codeine or even bigger things like that. But the point is you can have, as part of your control group, a comparison group who's receiving an existing treatment. And that goes back to our experimental group that I said I'd come back to and talk about. Our experimental condition, again, is the treatment condition in the experiment. It is the drug that we're looking to see has a new effect. It's what we're trying to see if the manipulation has a better outcome. Let's say we're trying to see if job satisfaction or benefits package relates to job satisfaction. IO psych type question. So there we're looking at if we want to see if a new benefits package we're introducing increases job satisfaction. So you'd compare that to the old benefits package. And the experimental condition then is the new benefits package. It is the one where we're looking for an effect in. This gets us to our manipulation checks. And this is where we're trying to directly measure whether the independent variable had the intended effect on the participant. And we do this, we can check to see if our manipulation was correct by explicitly measuring the independent variable. So again, we assign people to groups, but we need to make sure that that is going on. So we could explicitly measure, let's say we had people play a violent video game and a non-violent video game. Well, we can explicitly measure it by checking to see that the violent video game was actually played or the non-violent video game was played. But then you can also ask specific questions about the manipulation in a questionnaire completed by participants after the experiment, because quite often our independent variable, we want it to be a variable that we're deceiving the participants in some way. So if we ask participants afterwards, we can, in that case, try and find out if they could determine whether the manipulation occurred. So it's particularly important when there is participant manipulations going on, especially when there's subtle manipulations. The examples I've been giving so far are pretty big. But let's say if we're trying to do a subtle manipulation by just doing some priming. So we tell one group that we know people that are like them are bad at math. And we tell the other group we know people that are like them are good at math. That's a pretty subtle manipulation when you're using it in a paragraph of instructions. And you want to make sure that that got across and that the participants actually heard that. So when we're doing things like placebo controls and simulations, it's also important. This gets us to our last learning objective, which is to consider the ways in which consider the ways to increase external validity in an experiment. So what can we do? Well, one of our problems with the true experiment is the more control we have, the more internal validity we have, the more damage it does to external validity. Meaning, if you'll recall, external validity is how well we can generalize our results. So external validity, generalize. Generalizability. So our generalizability of our results is our external validity. Our internal validity is our control. You'll recall when we talked about comparing and contrasting these, that as we increase internal validity, as we control more, we decrease our generalizability because we've basically pushed people out of being potentially our results potentially applying to them. So one thing we can do, instead of doing a true experiment in a lab, we can do a simulation instead. So this is where we create the conditions within an experiment that closely duplicate the natural environment of behavior. So you get both mundane realism and experimental realism there. So this is kind of what I did in my experiment. So I told you for my couples experiment, I brought them into the lab, and then I told them they had to wait in a waiting room, and I sat them in a room that looked like a waiting room, was structured like a waiting room, and everything like that. And that's where the actual experiment happened. So even though I was in a lab, they at that moment in time thought they were not part of the experiment, and the room they were in was very like any waiting room you'd sit in waiting to do something. So in that case, a simulation occurred that basically closely duplicated the natural environment for the behavior, which would be anytime you're in just a public setting with other people around. So the waiting room, there were other people in the room, so there's other people around, so manipulating that setting. You can do true field studies. So this is where you conduct research in a place that participants or subject perceives as a natural environment. However, there is advantages. It allows researchers to investigate more lifelike situations, which is really good. That increases external validity. However, the disadvantage is it allows nature to intrude, reducing the amount of control and reducing internal validity. Because we've reduced our control, we are not getting as much, we are not controlling for as many extraneous variables, so we're reducing our internal validity. Okay, as I said, a pretty short one. So we covered explaining the goal of experimental research strategy, listing the 4 basic elements of experiments, differentiating the different types of variables in the experimental research strategy, examining the problems with causation, explaining the purpose of control in an experiment, explaining the purpose of manipulation in an experiment, and considering the ways to increase external validity in an experiment. However, it comes at the cost of internal validity. Thanks, come on back.